The central limit theorem. You all probably heard of this. Even if you never taken even an undergraduate course in probability theory, I'm sure you heard of this. Maybe you do not know exactly what it says, but it can be argued that this theorem is the fundamental theorem of probability. Every area of math has a fundamental theorem. This is the fundamental theorem of probability, though people call it the central theorem as opposed to the fundamental theorem. And the purpose of today's lecture is we're going to introduce the central limit theorem, and we're going to apply it to random walks. So this is what we're going to do. I'm going to state for you the central limit theorem more generally as well, but we're not going to prove the general version. We're going to prove the version for random walks only, because that's what we're going to be dealing with. But it's nice to know what the general version says. Let's recall our notation before we say anything. So recall that we have a sequence. These are independent random variables, and the probability of each of these. So you think of these as representing coin flips, but instead of encoding a coin flip heads and tails as 1 and 0, we rather encode it with plus and minus 1. And these are fair coin flips, so each of them occur with probability 1/2. So this is the setup, and then a random walk is this sequence that starts at 0 instead, where W0 is equal to 0. So this is initially where the random walk begins. It could be argued that initially it's not a random variable because we know what number it's equal to, though under our definitions, a random variable is just a mapping of the sample space to the real line. So we're just saying this is the constant mapping. And Wn, and for n greater than or equal to 1, we define Wn to be its initial value, in this case it's 0, and then we add these independent coin flips. So if our random walk starts at 0, then you can just ignore that part, and then the random walk up to time n is the sum of n independent coin tosses, and then the idea is that you're located starting at 0, and then you randomly move left or right, and this is your random walk, and you end up somewhere, and Wn represents where you end up if this process takes a total of n steps. So I just like to always go through this again so that people do not have to go back to previous videos to look up the notation and the definitions that we're using. Now, I also want to say that the average of the first n tosses is, let's call this an, the average. So the way we find the average is you sum up the numbers, and then you divide by how many numbers you have. That's the way you find the average. And the average can also be written as Wn divided by n, because the sum of these is Wn. That's the way Wn is defined. So that would be your average. And the strong law, well, the law of large numbers, there's two versions, the strong and the weak law, but they both basically say the same thing. They say that if n is large, I'll put large in quotation marks because I'm not trying to be mathematically precise here. It says that the average should be approximately 0. And if you replace the average by that, you're saying the random walk up to time n divided by n, whatever that is, that should be approximately equal to 0. So there's two ways to interpret the law of large numbers. There is the strong version, which says that if you create a little margin of error around 0, then the probability of falling outside those bounds goes to 0 as you increase the n. That's what we call the weak version. The strong version says something a little bit differently. The strong version says that if you consider the sample space of all points for which this limit does not go to 0, then the probability of that happens with probability 0. So that's what they say. And I wanted to just give you a little bit of a warning here. So it appears that Wn and the average Wn over n are very similar. Because after all, this is the same random variable, but it's just being rescaled by a factor of n. But however, the statement that Wn is approximately 0 is not true. There is no law of large numbers for Wn. Let me just show you some very simple computer simulations, and then we'll look into the math of what's the explanation there. So I'm going to create independent coin tosses. I'm going to sample from the number -1, 1. So I write down the list of numbers. How many do I want to take? Let's say I want to take 100 numbers, and replace is equal to true. This just means that after I pick a number from this list, let's say I pick -1, I put -1 back into the list, and then I repeat the experiment again. So that will be a random number generator, and it will select 100 random coin tosses, but you want to sum these up. So if I then tell it, if I put the command to sum all of those, in this case it's going to be 6. So let me do this again. So as I've said, the way you repeat a command, you look at your arrow keys and you press the up arrow key and you just repeat the previous command. If you press the arrow key again, you repeat the command before that, but this is the one we're going to use. So the random number generator will, as you do it, as you can see, sometimes you could get 0. I mean, 0 is the most likely number to happen, but it is the most likely, but it's still fairly unlikely. Here you're getting -18. This is quite far away from 0. This is far away from 0. This is far away from 0. So as you can see, I mean, here you're getting 30. This is really far away from 0. So these simulations should convince you that there is no law of large numbers when you just look at, if you just look at the random walk. However, if you take the random walk, so this over here is W100. Okay, this is W100. And now we're going to divide it by n, where n is the time of the random walk. Here we're taking 100 steps. If you divide it out by 100, and then you look at this, then look at that. You're actually getting something that's fairly close to 0. You do it again, you can see that when you rescale it by n itself, then this is illustrating for you the law of large numbers. There's not much deviation from 0. The deviation from 0 is very small. So these random variables are actually quite different, even though one is a rescaled version of the other one. So the law of large numbers is true for this one, but it's not true for just Wn by itself. And here's a very simple heuristic. Here's a very simple heuristic explanation for this. If you want to measure how unpredictable a random variable is, you look at the variance. The variance tells you the spread of it. A constant random variable has variance 0. It's completely predictable. So let's look at the variance of Wn. Well, the variance of Wn, that would be the variance of these independent coin tosses. And the variance of the sum is the sum of the variances if the random variables are independent. And now if you think about it, you can work this out, but if you just think about it, these random variables, they produce for you, let's draw a picture. So here's the number line, here's 0, and these random variables produce to you only 2 outcomes. It's either +1 or -1, and they happen with equally likely probabilities. So the expectation of this x is 0, but it's equally likely to either go left or go right. So on average, how much does it deviate by? Its square distance. Well, it's always 1 no matter what happens. So the variance of this, the variance of each of these is equal to 1. So the variance is equal to n. Okay, so you can see that the larger the time, the larger the variance. However, what happens when we look at the rescaled version? So the rescaled version, it's the version where you average out by the number of tosses. So then this would be the variance of Wn divided by, now this is a constant. And when you're dealing with the variance, your constant factors out with a square. So that would be n squared. So you end up with n over n squared. So we have 1 over n. And what you notice about this number is that this number is going down to 0. As you increase the n, the number is going down to 0. So this is a heuristic explanation for why it makes sense why this one is why this one is predictable for large n, whereas this one is not very predictable. Now you can be a little bit more general. You can be more general. And I think I'll put this on the homework problem, and you can go ahead and you can prove this. You can show that if an exponent, let's say alpha is the exponent, if the exponent is greater than a half, then Wn over n to the alpha is approximately 0. And let's do this in the weak sense. So what we're saying is that the sequence Wn over n to the alpha converges to 0 in what we say in probability. If you looked at the previous homework assignment, it discussed different modes of convergence. One can converge in probability, one can converge almost surely, one can also converge in different ways, but you will prove, and it's really almost the same kind of proof, that this random variable, that this sequence, as long as the exponent is greater than 1/2, will converge to 0 in probability. It's almost the same identical proof. You may wonder whether this convergence is also true almost surely, but when I try to go through the same steps that we did before, the proof did not generalize. So you may wonder, I guess it's an interesting question to think about, whether this convergence is still true almost surely as well, because maybe the proof does not go through, but nonetheless, maybe it's still true. You just have to use a more elaborate proof technique. But this is something you'll be able to prove. And as a heuristic, as a simple check, of course, this is not a proof, but this is just a way to convince you why this is true. As a simple check, if you look at the variance of Wn over n to the alpha, using the same procedure as before, the variance of the random walk is n, and then you have to divide it by n to the 2 alpha. It gets squared. But you see, alpha is greater than 1/2. So 2 alpha is a larger number than n, right? So this goes to 0, since 2 alpha is greater than 1, because the exponent downstairs is larger than the exponent upstairs. The exponent here is 1. So, and you can show that. There's actually nothing special about the n. You can replace this by a smaller power. You still have the same result. So that's a quick reminder of what the law of large numbers says. Now, before we write down the central limit theorem, I want to let us recall the binomial random variable. Why? Because the central limit theorem is often introduced with the binomial. You're basically saying the same thing, but some of you perhaps have seen this in an undergraduate course, and I want to talk about this very quickly so that you understand the connection. So it's very, very simple that you have two independent sequences. This is the sequence, this is independent, and the probability that x is plus or minus 1 is a half. And if you set Wn to be the sum of the first n of them, that gives you the random walk up to time n. So this is what we're doing, and this is what we call random walk. In undergraduate probability courses, this is displayed a little bit differently. You have a collection of random variables yi. They are independent, and these are coin tosses, but rather than plus and minus 1, you rather say that the probability that y is 0 is a half, and the probability that yi is 1 is also a half. So the distinction here is that these y's are binary. They're just 1 and 0. And you can easily create the sequence by rescaling these. So if you were to take xi, you were to double it, and then you were to subtract 1, then let's see if that will do it for you. I guess I have to add 1. Let's see if this works. So if x is equal to 1, then this is, no, I have to divide by 2. That's what I have to do. So if I take the x, and if it's already 1 and I add 1, that's 2 divided by 2. That will give me 1. And if x is negative 1 and 0, so that will give me 0. So you can easily construct these random variables by just translating these and rescaling them by a factor of 2. So that's not a big deal. So that's how you get the y's. And you can then define something called Bn to be the sum of the first n of these. So this is called random walk, and this one is called binomial, I guess they call these trials. What is this supposed to represent? Well, you see, every single one of these is either 1 or 0. And you think of 1 as being success, and you think of 0 as being failure. Now, what is success and failure depends on what you're doing. So if you're trying to keep track of how many defective computers you have, that's the quantity of interest. The quantity of interest is what you define to be a success. So a success is not necessarily something that's good in the real world. It's just whatever you're interested in observing. It could also talk about, let's say, the death of people. If you have n people and they all are sick with something, and there's a probability of death with a certain disease, then you could be interested in counting, observing how many deaths occur, and then you would define that as your success. So this is like a success in the sense of observations. So this is telling you, basically, this random variable, this tells you how many successes occur in a total of n trials. So the trials here are how many total attempts you make, where each attempt is independent of each other attempt. And this is the way this is introduced in an undergraduate probability course. You see this random variable quite a lot. Now the differences between these random variables is, so Wn and Bn are almost the same. They just have rescaled versions of each other. Wn ranges between all integers, I, where I is between n and negative n, and I has to be the same parity as the number n. Okay, so what that means is that if you're looking at W100, then the possible values that the random variable will produce for you will go from negative 100 to 100. So it'll be all integers between negative 100 and 100, and because 100 is an even number, it will be all even integers between negative 100 and 100. whereas Bn ranges between all integers I, where I is between 0 and n. There's no parity requirement here on the I. So that's what the situation here is. And if you want to know the probability that Wn is equal to one of those integers, the way you would do it is, we talked about this before, it's 1/2 raised to the n, and then it would be n choose n plus I divided by 2. You can also, because of symmetry, you can also write this as n minus I divided by 2. They're both going to give you the same thing. And this is why you want I and n to be the same parity, because then their sum is divisible by 2. This is the way you will calculate the probability that the random walk takes on that particular value. But if you're using the binomial notation, then you would say that the binomial being equal to one of those integer values, the probability of that happening would be 1/2 raised to the n, and then you would have n choose I. So in the binomial notation, it is a little bit simpler, but the price to pay when you're dealing with the binomial is that the expectation of the binomial is not 0, whereas the expectation of this one is 0. The expectation of the binomial would be n divided by 2. And sometimes when you're doing calculations, it's more convenient to have expectation being equal to 0, as the math works out nicer. And of course, here we're assuming that these individual trials have equal probability. More generally, it would be p raised to the I, 1 minus p raised to the n minus I, and then it would be n choose I, where p, so here, this is what would happen if the probability that that one of the y's, I'm not going to put an index on it, so the probability that one of those y's, so y is 1 or 0, is equal to 1. So success happens with probability p, and failure happens with probability 1 minus p. So if you have a total of I successes and n trials, then you will have I appearances of p, and then you will have n minus I appearances of 1 minus p, and you will have this factor, the number of different combinations that one can have. If it's symmetric, if the success and failure are equally likely, then this is a half, that is a half, and when you combine them together, you get 1/2 to the n. So this is just to bring up something that maybe some of you have seen before, so that we understand the similarities between random walks and the binomial, to show you that if you've taken undergraduate probability theory, then what we're about to do is going to be completely reminiscent, just in a different notation. Now, the central limit theorem, is to consider, let me say, the special case. The special case of the central limit theorem. And this was historically what was done at first, historically first considered, before mathematicians generalized it. So this is the special case. Is you're going to consider the following random variable. It's going to be Wn divided by the square root of n. Now, this is exactly where the law of large numbers breaks apart. So recall, I just told you a moment ago that if you have Wn over n to the alpha, and alpha is greater than 1/2, then the variance of this goes to 0 as you increase the n. And you have a law of large numbers for this. This converges to 0, at least in the weak sense. But what would happen if you set the exponent to be 1/2? Then the expectation of this random variable is 0, because the expectation of the walk is 0, and the variance of this, the variance in the numerator is n, and it's the square of the denominator. That would be 1. Now you're getting something that no longer goes to 0 anymore. So look at that. It no longer goes to 0. And so this is a random variable with expectation 0 and variance 1. So Wn over the square root of n is a random variable with expectation 0 and variance 1. Now, can we think of a random variable that has those properties? Yes. So that random variable is what we call, well, the standard normal density function. And the central limit theorem basically says, we'll make this more precise, that this random variable converges to normal 0, 1. So this is, well, the distribution of this is normal 0, 1. Now, how do you make this more precise? How does one make this more rigorous? So here's how we're going to do this. So let lowercase phi of s be the standard normal density function. So then what we're saying is, so this theorem that we're about to write down, this theorem goes by the name of the de Moivre-Laplace limit theorem. As you will see, this is the simplest version of the central limit theorem. Before mathematicians discovered the central limit theorem, this is the simpler version that they had. So the simpler version says, we're basically saying that this random variable, as you increase the n, it becomes normal. Now, how do you make this precise? What way you make this precise is you say that if you calculate the probability that this random variable falls between two real numbers a and b, and by the way, if you want to, you can also allow b to be positive infinity. So these could be extended real numbers as well. And I'm using a weak inequality here, but if you wanted to, you can also make them be strict inequalities. It's not that big of a deal. You're going to consider the limit as n goes to infinity. You're going to calculate the probability of that event. And the probability of this can be calculated by using the normal. So this is going to be the probability that a normal random variable called, let's call it gamma, is between a and b, where gamma follows the normal 0, 1 distribution. If you're confused by what this means, actually, let's not call it, let me call it z, a random variable z, where z follows the normal 0, 1 distribution. This is often the notation that people use for normal 0, 1 by this letter z. Standard normal is between 0 and 1. And what does this mean? This is just another way of saying, if that bothers you, this is just another way of saying it's the integral from a to b, and you integrate the standard normal density. So if this bothers you, you can, if you want to, you can just delete this and say that the limit of this probability converges to, and the limit to this. But the reason why I put it in here is because I'm trying to tell you what it means for this to converge to normal 0, 1. So what we say in mathematics is we say that Wn over square root of n converges So this is a different type of convergence. So we talked about convergence in probability. We talked about convergence almost surely. And now we have a third type of convergence. This is called convergence in distribution. What does it mean, converges in distribution? It converges in distribution to z. And what is z? Z is the standard normal distribution. What does it mean to converge in distribution? It means exactly this. If you're interested in calculating the probability that this falls within a certain interval, right? So you have to kind of go back to the definitions all the way back. What does it mean to be a random variable? A random variable is something that takes a Borel set and it pulls it back to a measurable, to an event in your probability space. But when dealing with Borel sets, you can just restrict all of that down to intervals, because the Borel algebra is generated by intervals. So you are taking an interval from A to B and you're pulling it back into your probability space, and you're calculating the probability of that event. And then you're taking the very same interval and you're pulling it back into a different probability space where you have a different random variable z, and you're calculating the probability that random variable falls in there. And if that random variable follows the normal 0-1 distribution, then this probability that you get here would coincide with that one. So that's what we mean converges in distribution. But this is what it says more carefully. So let me illustrate an example for you of this theorem. So here's like a very simple example. Let's just say a little bit of history about these people. So De Moivre was a mathematician who lived in the 1600s and 1700s. Maybe you've heard of him. He had a number of pretty nice mathematical contributions, especially that far back ago, where you barely had calculus back then. But he had a lot of nice mathematical contributions from that time period. And Laplace, I'm sure you all heard about Laplace. Laplace lived in the 1700s, 1800s. And they both discovered this theorem. De Moivre found it first, and then Laplace written about it. You may be skeptical and you may say, is it possible that Laplace stolen De Moivre's idea so he can say he discovered it? It's possible, but probably very unlikely, because let me just quickly look up where De Moivre lived. I just want to look up on Wikipedia where he lived. If they lived in different countries, then that would be less plausible that Laplace knew anything about it. So let me find it for you. Okay, so there it is, De Moivre-Laplace limit theorem. So the theorem appeared, doctrine of chances, De Moivre. So he is, where is he from? So he's from France and England. And it's a book that's written in English. Yeah, so this is where it first appears. It's called The Doctrine of Chances. And he proved the special case. And Laplace lived after him. Can't find anything on Laplace. But yeah, he does precede Laplace. So you could say they're both from France. Is it possible that Laplace stole it from him? It's conceivable, sure. But it is written in English. Laplace wrote in French. People back then often did not ever come across or even know about that they exist together. And the two versions are presented differently. So that's why we think they discovered it independently of each other at different times. Laplace did not know about it. But yes, if you're doing it chronological order, De Moivre, then Laplace. Let me show you an application, a very simple application of how you would use this. This is an example that one does in undergraduate probability theory. A true/false exam consists of 100 problems. In order to pass, the student needs to answer at least 70 questions correctly. What is the probability that the student passes by random guessing? And this example will appreciate to you why we need a central limit theorem and why the law of large numbers is not sufficient to solve this type of question. So let's see how this goes. One way to do this is you can let B 100, because it's 100 problems. This is the number of successes. And successes here just means correct answers in 100 trials. So this is a binomial random variable. 1 or 0, you get it right, you get it wrong. And what we want is we want the probability that this random variable is at least 70. Okay? And the exact answer, so it would be a sum. So if this random variable is at least 70, consider all possible values that this random variable can take. That means you got 70 questions correct, maybe 71 questions correct, all the way up to 100. So this would be the probability that this random variable B100 is equal to I, where the integer I goes from 70 to 100. And if you work this out, this is the sum that I goes from 70 to 100. And the probability here would be, it would be 100 choose I, and it would be 1/2 raised to the 100. So as you can see, this is something that's very difficult to calculate, especially in the 16 and 1700s without an access to a computer. Nowadays, with a computer, all of this stuff is substantially easier. So let's calculate this using Wolfram Alpha, just so we get to see what the answer is. If these numbers get even larger, if this was like 20,000 or something, then this becomes, at some point, the numbers get too big that the computer cannot calculate them for you anymore. But here, I'm going to tell it to sum 1/2 to the 100, choose 100I from I is equal to 70 to I is equal to 100. So this is, as you can see, it's amazing. It just instantly finds for you the exact probability. So this is the exact probability. As you can see, there's the number. Let's write it in scientific notation. So we have 1, 2, 3, 4, 5 zeros, and then we have 92. So let's go ahead and write it like this. So this is going to be about 3.92 times 10 to the negative 5. So not very plausible for that to happen. It's not like winning a lottery, but it does show you that this exam is difficult to pass by random guessing. Now, let's just say this. So let's convert it back. So let's convert this problem. So in the language of random walks, you would say this is the probability that the random walk in 100 steps. So now let's carefully think about this. If you have 70 correct answers, that's 70 heads, and 30 tails, when you're doing it in the language of random walks, that would be 70 times you see +1, and 30 times you see -1. So the difference between those is 40. So you want your random walk to be at least 40. And in order to use the Laplace-de Moivre theorem, you would have to, well, actually, let me do something for you before we calculate what this probability is. We could try to use the concentration inequality to estimate it from above. So we could say that this is equal to the probability that the random walk over 100 is at least 0.4. And this probability is less than or equal to, so the concentration inequality that we had a factor of 2, but the factor of 2 was because we had absolute value, had the symmetry. Without the absolute value, it would just be E. So the correct factor that I was missing was I had to divide this out by 2, where the epsilon indicates the margin of error away from 0. So in this case, this would be 0.4. This would be 0.4. And the n here, n is 100. 100 squared. So let's do this calculation on Wolfram alpha to see what we get when we do that. We have exponent negative 100 squared times 0.4, and let's put extra brackets just to be extra safe, divided by 2. Oh, I'm sorry, I put the square on the wrong one. This is just, yeah, it's the n is here. This is the one that's being squared. So 1, 2, 3, 4. So it's 3. So this one is, this is what you get from the concentration inequality. It's 335. Okay, 335. So what I meant to say, I put the square incorrectly. I meant to put the square on this one. This is bounded by 3.35 times 10 to the negative 4. So you can see that this does not compute the probability, is just overestimates it. It's not a bad overestimate. I mean, it is just one order of magnitude higher than what it actually is. But it does not actually calculate for you the number. Okay? So the concentration inequality is just an inequality from up above. You want to actually calculate what that number is. So this is the reason why our previous lecture about putting bounds on that is not the law of large numbers and all that stuff that we've talked about. Even though it is correct, it just does not help us solve this particular question. So let's calculate, let's estimate the answer using the de Moivre-Laplace limit theorem. So we can estimate this probability using the limit theorem. And it would say that in order for you to use it, you have to first rescale everything by the square root of n. So in this case, it would be the square root of 100. So you would rescale everything. So you divide it out by 10. And the limit theorem says that this is approximately equal to, it becomes accurate completely in the limit. Okay, but what is it approximated with? Because here n is a finite number. What is it approximated with? It would be approximated by the integral from 4. Well, this would be the probability that z is greater than or equal to 4, where z is the standard normal random variable. So this would be the integral from 4 out to infinity of phi of s ds. Now you can look this up either using R software or Wolfram alpha. Let's first do this on Wolfram alpha. I'll show you both ways how to do it. So using Wolfram alpha, this is the way you would type it in. You would just type in standard normal, and type in the number. So in this case, we want 4. So, and it shows you, do you want your random variable z to be smaller than 4, greater than 4, in absolute value greater than 4, and absolute value less than 4? So this is called left tail, right tail, two-tailed confidence. Which one do we want? So we want it to be at 4 and beyond. So we want z to be greater than 4, and it calculates it for us to be 3.167 times 10 to the negative 5. So that is what we're getting. So it's getting us that this is 3.17 times 10 to the negative 5. And if you were to compare this one to that one, that is a lot better. That is much, much better. The concentration inequality is just putting an upper bound, but this is a lot better. It's an upper bound, just be careful. This is 10 to the negative 4, whereas this is 10 to the negative 5. So do not carelessly just look at the numbers. Okay, so this is what we have. That's a little bit better. If you're wondering how you compute this, this was done on the homework for you. Just a quick recap of how this would go. We introduced this function capital phi of s, which was 1/2 plus integral from 0 to s of lowercase phi. And there was like an infinite series for it. And that's the way you calculate it. If you need to calculate this integral up to some number, it's going from 4 to infinity, but you can use symmetry to make it be finite and all of that. And then you express the answer using this function capital phi, which is the cumulative one that calculates the area up to s. And then you use the infinite series to calculate out the number, and this is what you end up with. So if you're wondering where that number comes from. There's also a way to do this using R software. So let me show you how you would do this using R software. So the command is, so question mark P for probability, norm for the normal random variable. And it shows you how to do it. It says P norm, and you specify where you want it to be. So if I write P norm of the at 4, and the expectation and the variance. So I think if I just write this, so that's giving me the left tail, the one on the left. If I want the, so by default, it's giving me the lower tail. If I want the other tail, I could just take the complement of that. So that's the way you would do it. It's the complement. And this is exactly what you're getting when you're using Wolfram alpha. This is the order of magnitude 10 to the negative 5. So this is what we got when we did that. So anyway, so this is the probability that you get when you estimate it. Now, I'm going to show you a very interesting trick to increase the accuracy. So you can make this be a lot more accurate. You can make this approximation be a lot more accurate by using something called the continuity trick. It's based on the idea that the random variable, the random walk, it's integer valued, whereas you're approximating it with a random variable that is real valued. So this one is sensitive to small changes, small perturbations of this number, whereas this one is not, because it's integer valued. So the trick is you're going to replace, so we had the probability, this is the way it started, we wanted to find the probability that W100 was greater than or equal to 40, and you were going to replace that by the probability that W100 is, you're going to use a half integer instead. Now, you can either go up or down, and let's just reason this out. If I write this, then that would not be correct. If I increase it by half, that would not be correct, because I'm excluding the integer 40 from the calculation. However, if I write 39.5, then that's exactly the same thing, right? This is the exact same probability. It does not change anything because 39 is excluded, whereas 40 is included. And because this is an integer valued random variable, you're not changing the probability. So you use a half an integer to use this continuity trick, and then you're going to recalculate the answer not by using this, but by using this. And then you would say that this is the probability that W100 over the square root of 100 is at least, you divide it by 10. So by dividing out by 10, that would be 3.95. And then this would be approximated by the integral from 3.95 up to infinity of phi of s ds. And now I'm going to calculate what this is using our software, where it's the same thing. I'm not going to even switch the screens. It's exactly what I did before, but instead of the number 4, I'm going to use the number 3.95. And when I do that, I end up with that this is 3.91 times 10 to the negative 5. How does that compare? Look at it. This is quite amazing. Look at how good this is. This is pretty amazing. Let's even put an exclamation point for how good that approximation is. How much are we off by? So this would be 6, 7. So 10 to the negative 7. We're off by 10 to the negative 7. So that is a pretty amazing approximation. And this kind of illustrates why you're not using the concentration. Concentration inequalities are not to calculate the tail for you. They're just to estimate the tail for you. This one is actually to calculate what it is fairly accurately. And in the old days, people made a table for these probabilities by calculating out the infinite series for this one carefully by hand. So they made a table, and all of these probability questions that require you to use the binomial can be converted back to this table of values that have all been pre-calculated. And so you made it easier to do these kinds of computations. So this is the illustration of the central limit theorem. And you can see it's quite amazing that we're only using n to be 100. It becomes even more accurate as you keep on increasing the number n. So that's the central limit theorem. And one of the questions that you can ask is, this is sort of like a good question to ask, is how accurate is this approximation? So this is something we will skip, because we do not really care about it so much. It's not really going to matter for the purposes of our class to know how good the approximation is. But it's like interesting questions to ask, like when you're just using the central limit, when you're using Laplace limit theorem directly, how good is it? If you put in the continuity correction, how much better is your approximation, putting all sorts of bounds? It's essentially sort of like the concentration inequalities all over again, where you're trying to put a bound on the error that you get. And that starts to become fairly tedious to work it out. We just want to prove the limit theorem. We're just going to prove that the limit as n goes to infinity will converge to the correct answer. As a question of how good the approximation is, that would be a totally separate discussion, which we do not want to get into. So the next thing that I wanted to talk to you about is the central limit theorem is actually much more general than what we're doing. It's not just random walks and binomials that can be approximated this way. It's much, much more general than this. And I want to talk about that first. Before we move on to the central limit theorem and the way it generalizes, I realized that it would be very convenient to show you a nice illustration of what we're doing on a computer. So let's consider this. We've said that when you take the random walk up to time 100 and you rescale it by the square root of 100, then this is approximately normal 0, 1. And I want to show it to you how it looks like in a particular graph so we can appreciate this a little bit more. This is what we're going to do. We're going to create this horizontal axis So W100, the possible values, so these are the possible values. At the very minimum, it's negative 100. This is when all of them are tails. And at the very maximum, they're all 100. And you're going to skip every other number. So this is 98, negative 96, all the way up to 98. So they have to be even numbers from negative 100 to 100. Now, when we rescale this by the square root of 100, then the rescaled version will go from negative 10 to 10, and you're going to skip by 0.1. So this is negative 9.9 all the way up to, I'm sorry, that would be 9.8, 9.8, 9.8, like that. So that's how you're going to be skipping in between them. And then what we're going to do next is we're going to create another axis. Okay, so this axis will represent the possible values associated with the random variable, the random walk divided by the square root of 100. And then we're going to create another axis going like this. And this axis is going to show the probabilities of each of those values. So it's going to range from some number from 0 to some number up to 1, and you're going to plot them. So like, for example, this number 10 would be very close to being at 0, because the probability that you end up, that this random variable ends up at 10 is when all of them are heads. So that would be 1/2 raised to the power 100. So that's almost equal to 0. And the same thing over here. And then you kind of plot them. You're going to plot these points, and you're going to get some kind of curve out of that. And when we get that curve out of that, on top of this curve, I'm going to juxtapose the normal density curve, and then you will see it's an almost perfect fit. And it's nice to see that done on a computer. So I'm going to bring up our software again, and we'll see how this works. First, I'm going to define a sequence starting from negative 100 to 100, and I'm going to skip every other number. Okay, so this is the sequence from negative 100 to 100. This is what the random walk does. And then the next thing I'm going to do is I'm going to create the probabilities. So y is going to be the probabilities associated with every single one of them. So it's going to be 1/2 raised to the power of 100, but then we have to multiply it by choose n plus x. X over here are one of these integers over 2. So that's what y is going to be. And then you can look at y. These are all of the probabilities. You can see this is incredibly unlikely to happen, the extreme cases. And in fact, that's exactly what happens when you do 1/2 raised to the power of 100. This is what you get. The one that's most likely to happen is the one that's located at the 51st position. It's not 50, it's 51st, because you technically have 101 numbers here. So it's the one in the middle. So this is 49, this is 50, this is 51. This one represents the probability that the random walk is equal to exactly 0. This is the most probable one, but it's not very probable. As you can see, it's still fairly small, but it is the most probable one. As a simple check, you can check that the sum of all of those numbers give you 1. They're supposed to, they're probabilities. And now I'm going to plot, and when I plot, you have to be careful. I'm not going to plot x against y, because when you're using the central limit theorem, it has to be the rescaled random walk. So it's really x over the square root of n. That's what we're plotting. So let's go ahead and plot that. And this is what you get. You get this curve out of this. And I can zoom out a little bit so you get to see this better. So this is the curve that you see. And it looks like the standard normal density function, but not quite, actually. Not quite. So I'm going to do this naively. I'm going to tell it to plot the, so this is the way you add a curve. So you're going to type curve, then I'm going to write add is equal to true. So add means I want to add this curve to this existing plot. Without putting this in here, what the computer will do is it will delete this picture and it will create a new picture. You want to add the curve on top of this picture. Well, let's give it a color. So let's use red. So you put red in quotation marks like this. You see, you write it in quotation marks, and when you complete quotation marks, it automatically makes it red for you. Just be careful, there's supposed to be one quotation. And now you have to add the curve over here. You need to write down the formula for the function. Now, what I'm about to do is going to seem a little bit unusual, but this is the correct way to do it. It's a bit unusual because if we scroll up, we already defined x as this list of numbers. The correct syntax for using curve is that it must be done in terms of the symbol x. That's the way it's programmed. So even though you already defined this x, you're not confusing the computer. The computer will not use the previous choices for x. This is just the required syntax. So the equation of the standard normal curve is 1 over the square root of 2 times pi. I'm going to multiply it by the exponential function, negative x squared over 2. And if we put this in here, you will notice there's something that's a little bit wrong. I'm going to zoom out so we see this better. You notice that we have a problem. It seems like it wants to fit, but the red curve is substantially bigger than the points that we have. So how do we explain what's happening here? So I'm going to go to the other screen and I'll explain it to you. And this is the confusion that has to do with probability and likelihood. In this particular case, this random variable, this random walk, this is a discrete random variable. It has a finite number of possible outcomes, and the numbers that you are plotting are the probabilities associated with those outcomes. However, when you have an absolutely continuous random variable, the interpretation is a little bit different. So let's say that z follows the normal 0, 1 distribution, then the probability density function of z is phi of s, where phi of s is this function. And this is the picture for the function. Now, what does this function represent? So phi of 1, what does this mean? So this is incorrect. So this is the wrong answer. You would say this is the probability that the random variable z is equal to 1. That is incorrect, because the probability that the random variable is equal to that it's equal to 1 happens with probability 0. Every absolutely continuous random variable will happen with 0 probability, because all you're saying is, what would happen if you were to integrate from 1 to 1 phi of s? That would just be 0. What's the probability of perfectly landing at the number 1 and nowhere else? When you're dealing with a discrete random variable, as in what we're doing, there's a finite number of outcomes, and one of those must happen every time you do it. So you could talk about an actual positive probability. So rather what it means, and this is what we were saying before, is you have to create a little interval around 1. This is 1 plus epsilon, and this is 1 minus epsilon. And you're rather going to ask with what probability you're going to fall into that. So you're going to rather calculate the probability that z is between 1 plus epsilon and 1 minus epsilon. And if you do that, then this will be approximately equal to phi at 1 multiplied by the thickness of your interval, which is 2 epsilon. It's how thick this interval is. So it would be 2 epsilon. And the smaller you make the epsilon, the more accurate this approximation becomes. So in a way, it's kind of like a derivative, because when you divide out by 2 epsilon and you consider the limit, it's exactly what a derivative does. So returning back to our picture, well, I took it down. But in this for this particular random variable, it ranges from negative 10 to 10. And the next one is 9.8, negative 9.8. It skips those numbers by 0.2. So you have to understand that this is really the thickness of the intervals that you're dealing with, and you're approximating it with an absolutely continuous random variable. So you have to put that adjustment in there. So let's put that adjustment in there, and then it will work out correctly. So let's look at, I'm going to clear this diagram, and I'm just going to repeat this again. So then I'm going to plot this, and I'm not going to plot the curve yet, but what I'm going to do is, let's look at x over the square root of 100. And notice the gap between two consecutive numbers is 0.2. So I'm going to plot the same curve, but I'm going to multiply this curve by 0.2, by the thickness of the intervals between. And now when we put it into our picture, now we have a perfect fit. as you can see. It's not a perfect fit, but I just mean perfect in the sense of what your eyes can see. The fit is so close that your eyes cannot even distinguish the error between the actual probabilities, which are these points and which are the dots, and the approximated probabilities, which are the points in red. Okay, and again, you cannot just plot the curve immediately because those are likelihoods. You have to properly rescale it so that it's calculating for you the probabilities of each of those numbers taking place. And this is what you get when you do that. So I think this is a very nice illustration that shows you a fit of the normal density curve being superimposed over the probabilities that arise from the random walk. And now that we've talked about this, let's go back and talk about the central limit theorem in general. So the de Moivre Laplace limit theorem is a special case of something much more general. Which is called the central limit theorem. So let's write down this theorem. And perhaps the most important theorem in all of probability theory. So here's what it says. It says, let xi be independent random variables with the same distribution. Now, they do not need to have the same distribution. That is not required. I'm going to state it this way first, and then I'm going to show you how you can generalize this even further. The reason why it's presented this way is because it's easier to state it in this way. So these are independent random variables with the same distribution. By the way, these random variables, they could be discrete, they could be continuous, or they could be more pathological. It does not matter. They're just independent, and they all follow the same distribution, with the same distribution, where the expectation of these x's, let's say that's equal to a. So you have to assume that the expectation exists, because otherwise it does not really make a lot of sense how you can apply the normal distribution, because the normal distribution has expectation and it has a variance. So otherwise the theorem will not make any kind of sense. So they all have expectation and they have a variance. And the variance, we commonly write it as, I'm going to write it as sigma squared. Some people write this by the letter mu. I'm not a fan of mu because it looks like a probability measure. So I'll just write A for average. We could write the number V for variance, but very frequently in probability theory, one deals not with the variance, but the standard deviation. And the standard deviation is the square root of the variance. So if you take the square root of that, that will be the standard. That would be the standard deviation, and then the variance is then the square of that. So this is how we usually write it. This is sigma squared. So we have independent random variables. They have the same distribution. They all have expectation and they have variance. And now we're going to construct the standardized average. So with random walks, we called it AN, which was just the sum of the first n of these. That's what it was. But here, I'm going to call this AN star because it's not your what you typically think of an average. It's a slightly different average. You're going to do this in a way so that you're getting something that has expectation equal to 0 and variance equal to 1. So the way you accomplish this is you're going to subtract NA over here, and then you're going to divide this out by sigma square root of n. That's the way you do this. So let me just do a quick check. So let's just check this. The expectation of AN star is, so it's the expectation of x1, which is A plus A. They all have the same expectation because they have the same distribution. And then you divide out. Now this is, of course, a constant, that's a constant random variable, so it just stays there. And then you divide it out. This is also a constant, so it just gets factored out. And that will give you 0, because this is NA minus NA. Then you can look at the variance. And when you find the variance, you calculate the variance of all of it. So the variance of x1, that's sigma squared, plus the variance of this one is sigma squared plus sigma squared. Now, and then the variance of this one is 0, because this is a constant random variable. And then you divide it out, and with variance, this constant gets squared. So it's sigma squared times n. So that will simplify to be 1. So the reason why you're setting up this quantity is so that you want something to work out that has mean 0 and variance 1. So this is what we call the standardized average. When you have a random walk, you do not put this in here because it's already 0. But we do, and the sigma is equal to 1, but we do divide by the square root of n. So this is what we have. And what we're saying is that then this sequence of standardized averages converges to normal 0, 1. And it converges in the sense of distribution. Actually, let me write it like this. And let z be a random variable that follows the normal 0, 1 distribution, and you're saying that it converges to z in the distribution sense. What does that mean? It just means that if you were to calculate a probability associated with this random variable being within an interval, that will give you the same thing if you use this one instead. So if you calculate the probability that the standardized average falls within a certain interval, well, it would be approximately the probability that this random variable z falls within that very same interval. But the way it becomes accurate is when you use a limit. So then when you use a limit, like in practice, like in applications, you just use the approximation. But the precise mathematical statement is that whatever this probability is, it will be equal to that. So then you can add over here for a less than or equal to b less than or equal to infinity. You allow them to be plus or minus infinity. That for any two extended real numbers, you can of course also replace the weak inequality by strict inequality. It doesn't really matter. The probability that this will converge to that. So that is the central limit theorem. And you should understand that this is a special case of what we're doing with the random walk. This is the generalization of the de Moivre-Laplace limit theorem, because as you can see, over here, if these random variables are plus or minus 1, which is what we've been doing, then the standardized average that we're getting is consistent with the de Moivre-Laplace limit theorem. Now, I want to just point out this condition. So it makes sense why we want them to be independent. It's very similar to the law of large numbers. If they're not independent, then it's very easy to come up with examples where this is not true. All you have to do is you pick any random variable that is not normal 0, 1, and you just repeat it as many times as you want. And then it's not going to converge to the normal distribution. It will be its own individual distribution, no matter what the n is, because it's the same identical random variable. So it makes sense why you want them to be independent. Do you need them to have the same distribution? Is this really a requirement? In the law of large numbers, at least in the weak law, we had a requirement that the variance does not get too big. We had the assumption that the variance was bounded. You have actually something similar with the central limit theorem, that they do not have to actually be the same distribution. You just have to say something about the variance, the way the variance behaves. It's going to be a little bit more difficult to state, but I just want to show you some numerical simulations for you. So let's go back to the computer, and I'll show you some simulations, and you'll get to see it. So let's clear all of this. We'll begin again. I'm going to let x1 be our unif. So these are uniform. These are going to be uniform random variables. Let's say we use 1,000 simulations. Okay, so these are uniformly chosen between 0 and 1. Okay, so that's what we have. These numbers are between 0 and 1. Then I'm going to do this. I'm going to do the same thing with this one. Okay, and I'm going to take their sum. I'm going to take, well, then I'm going to let A be the standardized average. So the standardized average is going to be, I'm going to add them up. I'm going to subtract their average. Now the average of this one is 0.5, right? Because these are numbers between 0 and 1. So the expectation for this one is 0.5. The expectation for that one is 0.5. So this is going to be 0.5, 0.5. So that's going to be minus 1. Then I'm going to divide by the square root of n, in this case 2, and I'm going to multiply it by the standard deviation. Now the standard deviation, I'll write it over here. So if x follows the uniform distribution on the interval from 0 to 1, then the expectation of x is just the midpoint of the two numbers. And the variance of x is, it's the length of the interval squared divided by 12. I believe I put this on the homework for you. It's a very simple calculation. You should take note that the variance only depends on the length of the interval and not on the location of the interval, which should make sense, right? The larger the interval, the larger the variance. So, and it's also, the variance has to do with squaring, so it makes sense why the square comes up. And the 12 is just part of a calculation when you do the calculus. So in this case, the length of this interval, these are uniform from 0 to 1, so the length of the interval is 1. So 1 squared divided by 12. So we're going to do times, square root of 12, like this. Okay? And now if you type in A over here, this is the simulation with 1,000 experiments, where you pick 1,000 numbers for x1, you pick 1,000 numbers for x2. These are being chosen independently, and this is your standardized average. And let's use the finite amount of data to estimate the density curve. So we're going to plot the density of A. Go ahead and do this, and you're getting something like this. I'm going to zoom out for you so you see this a little bit better. You're getting something that looks like this. It's only 2 of them. And actually, we've done this calculation before. This will really be a triangular distribution over here. But now let's plot on top of it. We're going to type over here, I'm going to type in curve 1 over the square root of 2 times pi times exponential function. We're going to add this to our plot with color red. Here you do not have to divide out by the length of an interval, because these random variables are continuous random variables. So we'll run this, and then you can see that if I was to zoom out for you, you can see that the curve in red is the true, the curve in red, this is the standard normal density, and the other curve that we have over here, this is the approximated distribution that they follow from the simulations. And now we just increase the amount of random variables that we have. So this is what happens when we have 2 of them. This is what happens when we have 3 of them. And then here we'll just add x3. This time we have to subtract 1.5. And instead of square root of 2, it's going to be square root of 3. And now let's rerun the calculation. Okay, and the fit should keep on getting better and better. So that's with, okay, let's do it for 4. So let's do it for x4. And I'll just add it over here. So minus 2. So this is square root of 4. And you should see that it's getting a lot better. You can get a more accurate picture by running more simulations. So let me just increase the amount of simulations to 10,000. And I will re-execute this again. And as you can see, that it's very, very good fit. You can keep on adding more. I'll do it for 1,000,000 for you really quickly. So this is what happens. Very good fit, as you can see. And it's just a question of having more of them. Already with just 4, it's a very good fit. And if you had 20 or 30, 50, it would be almost indistinguishable from the approximation. So that's the central limit theorem in action. Now, I would like to also tell you that it's actually not required that these random variables be identically distributed. You can make this one go, let's say minimum goes from -1, maximum goes to 1, okay? Let's say here minimum goes from -0.9, maximum goes to 0.9. For this one, let's type minimum goes from -0.8, maximum goes to 0.8. And here minimum goes from -1.1, and maximum goes to 1.1. So the average would then be, the standardized average would then be the sum of these. We have to subtract the expectation. Here the expectation is going to be 0 because I centered them at 0, so that's going to be the easy part. We have to divide out by the square root of n. In this case, that would be n. But we then have to divide out by the sum of the variances for each of these. So we have to find the variance for all of them. So let's say v is the variance. So this one will have variance. It's the length of the interval, so it would be 2 squared divided by 12 plus 1.8 squared divided by 12 plus 1.6 squared divided by 12 plus 2.2 squared divided by 12. So that would be the variance, and we're going to do 1 over the square root of n multiplied by the square root of the variance, because we're finding the standard deviation for the sum of all 4 of them. So if I've done this correctly, as you can see, I'm off by a lot. Maybe I messed up the calculation with, so it's the length of the interval divided by 12. So the variance for this one, it's the length of the interval, in this case 2, so I'm not sure what the issue here is. So if I was to take the expectation of A, it would be 0, because each of these has expectation 0. So if I type over here mean of A, that's the average of the numbers, that would be 0. And if I ask it to estimate the standard deviation of A, that should be 1. But as you can see, it's not 1. Or the variance of A. It's 0.25. So I'm not sure what the issue is. You can figure it out yourself. Let me do this. So because it's 0.25, what if I was to, let me try multiplying this by 0.5, see if it fixes the problem. I think I'm just off by a certain factor here. Yeah, it looks like I'm off by a factor of 2 somehow. I leave it up to you to figure out. But you can see that when I put in that, it's probably some small minor arithmetical mistake that I'm not interested to figure out. But when I put it in here, you can see that the standardized average that you're getting and the curve in red, which is the standard normal density curve, it's an almost perfect fit. And in this particular example, you should see what happened. We used 4 random variables. They all had a different distribution, and nonetheless, all of it worked out in the end. However, I want to show you what would happen if I keep everything the same, and I take x4, and instead of making it go from -1.1 to 1.1, let's say I make it go from -10 to +10. I'm going to get rid of the standardized average because we do not need it anymore, and I'm just going to plot for you the density curve. You're going to see that the density curve by no means resembles a normal curve at all. And the reason for this is because the fourth random variable, so let me do this. I'm going to get rid of the variance, okay? And I'm going to get rid of these rescaling. These constants are just to properly rescale it so it fits. We do not really care about the numbers. I just want to show you the shape, just so you get to see the shape. So this average, it's not a standardized average. So it's just going to be a normal curve. It should be a normal curve that's centered at 0, except it's not standardized to have variance 1. I do not really care about, I just want to show you the plot of this. It's not going to look like, so if I go back to the previous one where it was negative 1.1 and 1.1, if I let a be just the sum of these, even dividing by 4, it doesn't really matter. It's just not rescaled properly. But the shape of it, as you can see, the shape of it will still be normal. It's just a different type of normal that's not properly scaled. However, what would happen if I was to exaggerate one of these? If I make x4 go from negative 10 to 10, before we run the simulation, it should make sense that this random variable a should be a lot flatter, because x4 has a much larger impact on the sum than x1 to x3. You see, this one has numbers ranging from negative 10 to 10, whereas these numbers are not too big. So x4 has a much greater impact, overall contribution to the sum, than the first 3. So x4 is a lot more relevant. And since x4 is uniform, it's basically flat, it would mean that a would be flat except at the ends where the extremities are influenced by these 3. So if we run the simulation, you'll see what I mean. So there it is. There's the actual calculation that we get. Notice it has the behavior of what we're saying, that it's flat. It's sort of like uniform, which it's the way it's supposed to be because x4 is uniform. And then at the end, it has like this piece of it. This is sort of like the left piece of the normal, and that's the right piece of the normal. So it's almost as if you took a normal and you split it down the middle by a flat curve. And there you can see the central limit theorem does not work. But it kind of makes sense why it does not work, because the contributing random variable that we have here, x4, has a much larger impact on the sum than the other 4. Okay, so let's go back to our screen and we'll say how you can generalize the central limit theorem. So they do not have to be identically distributed. It's just that it's a little bit harder to say. So this is the theorem. In the theorem, we keep it simple and we say they have the same distribution. So I'll make a statement over here. So this version, I believe, not completely sure about this, this one goes back to a mathematician called Paul Levy, who observed, he's a mathematician associated with probability theory, and he observed that the De Moivre-Laplace limit theorem can be generalized in this sort of a way. And then people thought about, well, do you actually need them to have the same distribution? Maybe you allow them to have different distributions as well, but you want to be able to say that none of these random variables overpowers the other ones. So I'll just say this, that so we can eliminate the same distribution condition and place the, which I'm not going to write down because it's a little bit complicated. It's called the Lindenberg condition. Which basically says no random variable xi overpowers the others. And if you want to see a reference to this, I'm going to give you a reference and you can look this up. So there's a book, it's a graduate text in mathematics. It was, the name of the book is not very, it's a math book, so it does not have an exciting name. And it's just called Probability. So it's the most generic possible name you can think of. But the book is a very good book. and it was written by Shiryaev. I might be misspelling the name. The interesting thing about Shiryaev is he was a student of Kolmogorov himself. So he written this exceptional book on probability theory. It's a fairly advanced book. It's about 500 pages. And I recommend the old version. There is a newer version in 2 parts. So they divide it into 2 parts. So if you come across a GTM book and it's called Probability 1 and the author is Shiryaev, do not get that one. So the new version, it's called Probability 1 and Probability 2. It's not worth it. You're paying double. It's better to get the older version, which is just called Probability. There is no part 1, part 2. It's just probability theory. And this is the version that I recommend. And the theorem is stated, this theorem, this generalized theorem is stated and proved. The proof is about 25 pages long. So I'm not actually saying that when the author writes proof, it goes on for 25 pages. The author has to create a lot of, you can say, preliminary material that is used in the course of the proof. A lot of it has to do with analysis. It's analysis adapted to probability theory. The actual proof, I recall, goes like maybe 4 or 5 pages when I learned it out of that book. But the preliminary material takes a lot more. And the author is very good. He's very good at writing. He's very easy to follow. He's very clear. So that's what I would recommend for those of you who want to see it. So I'm going to give you a simplified version. So here is a simplified version of the Lindenberg condition, which is much easier to understand. And it says this: you assume that the random variables are all less than or equal to b. So this is boundedness. You assume the random variables are bounded, and you also assume that the sum of the variances, so if you add up the variances, then they go to infinity. So they grow to infinity. So essentially what this is saying is that these random variables never get too big, and at the same time, you never come across a situation, like think about what it would mean if the sum of the variances, well, let me just say it like this: the sum of the infinite series of variances is equal to, it diverges, right? It diverges to infinity. Think about what it would mean that if this infinite series was to converge. It would mean that the contributing random variables to the sum will have smaller and smaller and smaller variance, in the sense that they have a very small effect on the sum, on the standardized average. So this is the simplified version. The Lindenberg condition is more general than this, and you can look it up. But you would just replace it, the standardized average, instead of being minus NA, it would be minus the expectation of the first n of them, and then divided by the square root of the variance of the first n of them. That's what you would do. So if you can look that up if you're interested in this. Let us do an example. In this example, we're going to have 48 random variables. Why 48? Well, you'll see. The number makes the calculation simpler. They will all be independent, and they follow a uniform 0-1 distribution. And we're going to set S to be the sum of these 48. And the question we're going to ask is, what is the probability that their sum is less than or equal to, and let's make up a number. Let's say that number is 20. So what is the probability that their sum will be less than or equal to 20? Now let's just get an idea here that these random variables on average are about 1/2. That's their expectation. So if you were to add up 48 of them, then the expectation of this random variable s should be about 24. So this is a little bit smaller than what you expect s to be. You can also, if you want to, you can put an interval. You can say s is between 20 and 18. And it is possible to solve this problem exactly by using convolutions. We actually talked about this before, how you find the probability density function for a sum. So you will have to do 47 integrations, 47 because you start pairing the first two. So you would have to do 47 integrations in order to calculate this out. So clearly that's not a very good way of solving the problem, but you can get a very accurate estimate by using the central limit theorem. And the way you would do this is you would calculate the standardized average of the first 48 of them. So I know that the central limit theorem is really for a sequence of random variables, but in real life, in practice, the theorem always gets applied to a finite collection. So this is a finite sequence, and we would take the sum of these. So it would be s, the sum. Then we have to subtract away the expectation. In this case, it's 24. We have to standardize our average to make sure that the expectation is 0. And as we remarked, the expectation of s is 24. And then we have to divide out by the square root of the variance of s, because we want something whose variance would be 1. So each of these has variance 1 over 12, as we've said before, and there's 48 of them. So 48 over 12, so that would be 4. So, and then you divide out by the square root of 4, so that would be 2. So you would divide out by 2. So that would be the correct way to do it. And then you can check that the expectation of this quantity is 0, and the variance of this random variable is 1. So you've standardized everything. So let's just do this check one more time really quickly. The 24 plays no role, so it's the variance of s. So you add up the variances. Each one has 1/12. There's 48 of them. So that'd be 48 over 12, so that's 4, and then you square this number, which is 4. So 4 over 4, that gives you 1. And so by the central limit theorem, that A48 star is approximately normal 0, 1. So that would mean that now what are we trying to do? We want to find the probability that s is less than or equal to 20. So we have to put it in this form. So we would subtract 24 from both sides. So that would be less. So you subtract 24, so that's less than -4. And then we divide both sides by 2. Okay, and by the central limit theorem, this would be approximately the probability that z is less than or equal to -2, where z is a random variable that follows the standard normal distribution. And thus, the probability, the answer that we're looking for, is going to be the integral from -∞ up to -2, and you do phi of s ds, whatever number that is. In the notation that we've used before, if you go from -∞ up to 0, because the PDF is symmetric, it gives you half of the area underneath the curve, and then plus the area from 0 up to, oh no, sorry about that. That makes no sense. I should just leave it like this. So then you can just do this on the calculator. Whatever number that is, that's going to be your answer. So that's the way you do this. Now, a good question to ask is, how good is this approximation? This came up in a previous problem, which we saw the approximation was pretty good. And so there is a complicated theorem. It's called the Essene theorem. And if you want a reference, you can look at Shiryaev for that theorem, the precise details of the theorem, which I'm not going to make this precise, but it basically says, right, it basically says the error of approximation is bounded by 1 over the square root of n, where n is how many random variables you're using. So the central limit theorem, okay, so you have two theorems. One of them is the central limit theorem, which is not about approximations, it's about the limit. The limit is exactly converges to the standard normal. So that's the limit part of the theorem. In practice, however, we use a finite amount of random variables, so we're approximating it with a normal, and then the question becomes, how good is the approximation? So this is the Berry-Essene theorem that talks about the approximation with the normal, and it says it's bounded by 1 over the square root of n. So in our particular example, we're using 48 of them, so square root of 48. So that would be about 7. That would be about 7. So this would mean that this answer is within, so is this answer within 1/7 of the correct answer? Is that really what it is? Because this seems like a very bad approximation, because we are talking about probabilities. The numbers that we're dealing with, they're already smaller than 1. So that is not substantial. That's not a really small number in the universe of probability theory, because everything's bounded by 1 as it is. So this seems like a really bad estimate. So what you need to understand is the Berry-Essene theorem, when it's talking about the error of approximation, what it really is talking about, the worst possible error in the most general sense. So what happens is that the error that you're getting with approximating it with the normal will very much depend on the random variables themselves. So certain types of random variables, they approximate with the normal a lot better. If you want a simple, so basically it has to do with how thick the tails of your probability density function are, assuming it has a probability density function. So the tails, so you can have something that diminishes to infinity very slowly, and then you can have something that diminishes to infinity a lot faster. So we call those the tails. How thick are these tails? Or maybe the tails completely die out. Like when you talk about the uniform, there are no tails, they just become 0 eventually. So it has to do with the tails. So the heavier the tails are, the worse the approximation is. That's like the very simple version of it. So in this theorem, you're talking about the worst case scenario. So if you have the absolute worst type of random variable that you can possibly think of, and you try to apply the central limit theorem to that, then the approximation you will get will not be very good. But the random variables that appear in practice, so many of the random variables which are used in practice, the approximation is very good. So you can focus on different types of approximation inequalities depending on the kind of random variable you have. In fact, let me say this. If your random variables are already normal, then the approximation is perfect. Why? Because a linear combination of independent normals is another normal. It might be a normal of a different family, where it has different mean and standard deviation, but this is just a well-known fact that I referenced before, because when you're using the limit theorem, you're adding up, right? Like, what are you doing? You are adding up random variables when you're using the central limit theorem. So if the random variables to start with happen to be normal, then the standardized average that you're getting, it's a linear combination of those normals that have been standardized, and so it's going to be perfectly normal. It's not even an approximation anymore. So you can see that in the best case scenario is when the random variables are normal to start with, And in the best case scenario, there's no error whatsoever. And we saw the computer simulations that we were doing with the uniform random variable. We saw that by using 4 or 5 of them, the simulation that we were doing was almost indistinguishable from the standard normal distribution. So this just illustrates that the approximation very much depends on the kind of random variable you have. So when you see this kind of theorem, and it talks about this bound over here, and you see this is a pretty bad bound, it's a very slow rate of convergence, you just have to understand that this is the worst possible case that can happen. The kind of random variables that we often work with, not all of them, there are random variables in probability theory that are called the power law distributions. The power law distributions have thick tails. So for those ones, it would be a little bit more suspect to use the central limit theorem to approximate what is going on, unless you have like billions of them, because you would have to take the square root of that. So, but it really depends on what kind of random variable you have, but that is a good question to ask. You saw that the example that we were doing when in the de Moivre-Laplace limit theorem, even with 100 steps in the random walk, our approximation was really good. It was not 1/10 within the answer. It was more like 10 to the power -6 within the answer with the continuity correction. Without the continuity correction, the error was about 10 to the -4. So you can see it is doing a lot better than what the Berry-Assim theorem says. So you really should understand this theorem for the worst case scenario that can happen. So this is an example of this. Now I want to discuss some history behind this, some other history. In particular, why do some people call the normal distribution also the Gaussian distribution? So what does Gauss have to do with this? Why do we call the normal random variable sometimes Gaussian? So going back to history, de Moivre and Laplace limit theorem was to estimate the binomial random variable. And the binomial random variable is just a shifted version of a random walk. And then Gauss recognized, so Gauss asked this question. So Gauss observed that experimental measurements and he's not the only person. I imagine maybe Laplace also realized that, other people realized that, but Gauss worked on this, written about this, observed that experimental measurements follow a normal random variable. So the idea is that you take a measurement and you get a number, 12.3 units, whatever those units are. You take another measurement and then you get 11.6. You take another measurement, you get 13.4, and so on. That there's randomness that influences your measurements. So Gauss would say that you have the true measurement, and then you add to it what you call noise, random noise. The noise is the result of problems in the environment that mess up your measurement. So maybe if it's very sensitive equipment, if any dust lands on the apparatus, it will contribute to the measurement. So every small little factor that can mess up the true measurement. Now, why does it follow a normal random variable? Well, the reason for this is because the noise is really made out of lots of different contributing factors. So maybe we talk about dust that settles. How much dust? Is it more than usual or less than usual? Maybe there is air pressure at the moment of measurement has some kind of effect. Maybe humidity in the room has some kind of effect. Maybe if it's more humid, it absorbs more and it messes this up. Maybe the location of placement of the object on the scale. The scale isn't perfect, and where you put it on the scale might slightly mess up the measurements and all of that. And then there's the mechanism itself that has to round up or down to its best guess. And all of these, right? And then you can also talk about round-off error. I guess you can mention that round-off error, because the apparatus that you use to measure, it only displays a certain number of digits, and it has to make a choice to round up or round down. So sometimes you get an overestimate, sometimes you get an underestimate, sort of like a coin toss, heads or tails. You do round up or do you round down. So what you see is that noise is a random variable which is influenced by many smaller contributing random variables. Okay, so basically we're talking about a sum of independent random variables. That's what's going on. That in the central limit theorem, it does not matter if these random variables are normal or not. You're taking a sum of independent random variables. And when you take a sum of independent random variables, what happens? What happens is the noise factor that messes up your measurement is therefore a normal. It's a normal. And that allows you to estimate the measurement and put on it the uncertainty that you have. So basically it comes down to this. So when you collect measurements, so this is your data, you have the average, right? The average, this is what you estimate, the spread, and how many samples. And all of this influences your answer. So you take the average of all of the numbers. That is fairly simple to understand. If you have 20 measurements, which one should you pick? Well, the reasonable thing to do, and no fancy math is required, is you just take the average of the numbers. That's what people have always been doing. But the more important question to ask is, what uncertainty do you have? How much uncertainty does one have with that kind of estimate? So this is where the spread comes in. If the numbers are closer together, if there's less spread between your observations, then you become, on an intuitive level, more confident in the average. And also, how many samples you take. So if you're using 5 numbers to make an estimate, you're not going to be as confident if you use 500 numbers to take an estimate. So you really have to take those 3 quantities into consideration. And you can therefore ask the following problem. So how to construct a confidence interval for your estimate. So you make an estimate, let's say this is what you estimate, and you want to build an interval around it, and maybe you want it to be 99%. So this will tell you that there's a 99% probability that your average that you calculated falls somewhere within the true value. So that's what you want to ask. Because in scientific questions, you often have 2 competing quantities. So maybe you have one quantity, and then you have another quantity, and you're interested to know whether this quantity is bigger than that quantity. So you take measurements of this one, you take measurements of that one, and it could happen that maybe some of the measurements overlap. But let's say you take the average of these, you take the average of those. You may not know exactly where it is, but at least you can, if you build your intervals, you can be rather certain that there's enough separation between the intervals to assert that this one is bigger than that one. And that's often what you care about, because you may not know exactly where it is, but sometimes you do not care exactly where it is. You just want to know whether it's bigger than something, bigger than a certain threshold that you're interested in. So this is what Gauss observed, that you have to use the normal to solve this kind of problem. So let me illustrate for you a very simple example of how you would do this. So here's an example. So let us do an example where we have, let's say, 20 measurements, and we want to construct a confidence interval for the estimate. Okay, so let me do a simulation for you. This will make it easier to understand. So I'm going to generate, so let's make sure that we have the same numbers. So I'm going to set the random number generator to start at the seed of 1, and I'm going to generate some fake data. So I'm going to write R norm. So this is a random variable with a normal. We're going to have 20 samples. Let's say we set mean is equal to 1 and standard deviation is equal to 2. Okay. Now, when you do that and you look at your data, you've generated 20 random numbers from this random variable in an independent way. Now, here's the whole point here. So in real life, you do not know the mean and standard deviation. You want to estimate the mean from the data. You do not really care about the standard deviation. It's just part of the problem, but you often care about the mean. That you think of this data as representing measurements associated with some kind of experiment, and let's say the true value is 1. Okay, that's the true value. But the point is, when you take measurements, you're not going to get the true value. As you can see, sometimes you underestimate the true value. Sometimes you get somewhat close, and sometimes, so these are fairly close, and sometimes you overestimate the true value. So this happens. So what you can do is you can take the average of this. So if you just take the sum of all of those numbers and you divide it by 20, this is your estimate. So you're estimating that the mean, so the true value, is around 1.4, 1.38. You can see it's somewhat away, and that just illustrates the point that you cannot just take the average. So this is like the most reasonable estimate you can give for the true value, which in this case is 1, but there is some margin of error. So how do we quantify how much uncertainty that we have? So here's the way that we do it. So this is the way Gauss would solve the problem. Maybe not in the language of modern probability theory, but somewhere along these lines. So you would have x1 up to x20 be independent random variables, and they're all following a normal distribution that has a certain average, some number a, and some variance sigma squared. You do not know, so these are unknown. So that's something we need to understand. In a statistics problem, these are known. And we want to determine, this is what we want to estimate. We do not care about the sigma, it's just part of the problem. So the reason why these follow a normal has to do with the central limit theorem, right? That's the whole point, that because measurements are normally distributed, all of these samples that we take, these 20 samples, these 20 independent samples, follow from some normal, but we do not know what it is. So then we're going to form the standardized average. Okay, so the standardized average, let's call it capital A. We're going to take the sum of these. We're going to subtract away 20 times A. Okay, and then we're going to divide out. So in this case, we have sigma square root of 20. So this is what we have. And then, what's the idea? Well, then the idea is, so then A will follow a normal 0, 1 distribution. So in this case, the approximation would actually be perfect. The reason why it would be perfect is because these are already normal to start with. So it's not even an approximation. This is just a linear combination of normals. So that's going to be A. So, and so what do we do with that? So we have our A, and we can ask, for example, so let's ask something like this. So it's a well-known fact. So here's like a well-known fact. So if you have the normal 0, 1 distribution, that the interval from -1 to 1, it takes up 0.68 probability. And that the interval from 2 to -2 takes up 0.95. This is just a calculation. This is just a computation if you just calculate out what that area is using the infinite series, and these are the numbers that you find. If you're going from 3 to negative 3, then this now becomes 0.997. Okay, so often people settle for a 95% confidence interval because it's 2 standard deviations. That's often what people do in the real world. So it's up to you what level of confidence that you want. You can do 99%, but then the numbers are not as nice. We like nice, whole, round numbers. So let's ask this question. What is the, let us find a 95% confidence for the estimate. So the way we would do this is, what we want is we really are saying that the probability that the standardized average, if you're located between -2 and 2, then that would be 0.95. That would be 0.95. And then you put in the information that you have in your problem. So this is -2. So the standardized average was the sum of those random variables divided, so minus 20 times a, divided out by, what did we have over there? Sigma square root of 20 less than or equal to 2. Okay, so we're trying to say something about this number a. This is the mysterious number for us, and we want to, now we know what these are. So in our particular problem, the one that we're doing in our simulation, this is our data. Okay, so this is the data that we generated, and you can just add up the numbers that you have in that data. So if I just ask it to sum that data, it comes out to be 27.62. So this one is 27.62. So you have the sum of those, and you have square root of 20. But then what do you do with the sigma? What does one do with the sigma? So what we do here, and it's a level of how much complexity that you want, but you can estimate sigma naively. So how does one do this? So here's how you would do this. In actuality, it's more complicated than this, but here's what one would do. So as you can see, the sum of those random variables, of the realizations of those random variables, is this. But how do you get the estimate for sigma? So the way you would do this is, normally the way we find, so to find the variance of x, we can use the formula that variance of x is the expectation of x squared minus the expected value of x squared. So now the expectation is the average. So we would take the average, so that's the mean, the average of the data squared. So you just square all of the numbers in the data, and then you subtract the square of the mean of the data. Okay, and that's the number that you get. And to find the standard deviation, you take the square root of that. Okay, so if you take the square root of that, you get around 1.78. Okay, that's what you get. So this is a very naive way of estimating that sigma. So returning back to our problem, we would replace this number by that, 0.178. So then we have to, yes, and then you can go ahead and you can solve. You can go ahead and you can solve for that a. So you would say that. How do you solve for a? Well, you have to clear the denominator, so that's -2 multiplied by 1.78 times the square root of 20. Then you subtract 27.62 is less than or equal to -20a. And then here you have 2 times sigma times the square root of 20 minus 27.60. So all I'm doing is I'm just solving for a. So I clear denominators by multiplying this through, and then I add, and then I subtract away this number, and we're getting this interval. So we're saying the probability of this should be 95%. And now you divide everything by negative 20. So by dividing everything by negative 20, so let's just do these calculations really fast, just for concreteness, so we get to see what this is. So I have to do these on a calculator for you really quickly. So I'll just tell you what these are. So here I'm getting 43, negative 4354, the one on the left. And on the one on the right, I'm getting, so let me do that for you really quickly. So here I'm getting negative 11.60.70. And now you would then say that the probability that the true average, the A that you're trying to find, falls within that interval. We have to therefore divide out by those numbers. So let me just divide out for you. So you divide by a negative number. So this is 0.585. You just have to be careful when you divide by a negative sign not to forget to switch the order of the inequalities. So this is what I'm getting. So roughly something like this. So this is 0.95. So that's your 95% confidence interval. I know that some statisticians would not like what I did because I'm saying the probability that this unknown number falls within that interval is 0.95. They would object and they would say that this is either true or false. It's either 1 or 0. Yes, that's technically correct, but let's not even bother to go there. So this would be your 95% confidence interval, that you're estimating. So you're saying there's a 90. So the number that you're trying to estimate, the unknown number in this case is 1. There's a 95% chance that it falls somewhere within that interval. So you can see it's fairly large interval. It's not that great because we do not have that many samples. But the more samples you have, the tighter these intervals tend to become. But that's basically the way you do it. That's a very simple way of doing it. The reason why I call this a very naive estimate for sigma is because sigma itself is a random variable. When you're doing that procedure where you're taking a bunch of numbers and you're adding them up, you're always getting a different value for that sigma. So the estimate that we're using for sigma is itself a random variable. You can add some more complexity to it, and then your uncertainty is actually a little bit bigger. And in the statistics class, they discuss what happens there. That's what they call the chi-squared distribution, because sigma itself is not actually normally distributed. It cannot be 0. It follows a different distribution. So the actual interval is going to be a little bit larger, has to be a little bit larger. But this naive estimate is not that far off from what you would get if you were doing it a little bit more accurately. But this is just like a very simple outline of how one uses the normal random variable to make these kinds of experimental calculations. And this is what Gauss discussed in his work, and a lot of people started to refer to it as the Gaussian. One interesting thing that I noticed is that people that come from a mathematics background generally call these normal random variables, whereas people who come from a scientific background, many of those people refer to them as Gaussian. So I guess maybe it's more of an influence in the world of science than in the world of mathematics. But regardless, this is why we call it the Gaussian, and this is like an application of how the central limit theorem is used to find these. I should just say it is very possible that maybe I made some minor arithmetical calculation along the way, but I'm sure you can figure that out yourself. This is, after all, a graduate course. It's really the intent of the lecture that matters here. Now, what I realized is that we do not have time. We do not have time to prove the central limit theorem, even in the special case of the de Moivre-Laplace limit theorem. So what would make sense is we're going to do an additional lecture. So you can think of today's lecture as just an introduction to the central limit theorem, its significance, how it is connected with random walks, and then some of the applications of the normal. And now that we're comfortable with that, we can then talk about how one goes ahead and proves something like this.